All right, everyone, let's get started. So today I'm going to talk about the next lab. I haven't posted the lab sheet yet, but I will right after class. I'm still making some last-minute tweaks to it. This lab is kind of complex. The objective is to design or write low-level drivers for two of the peripherals on the ESP32. So I'll probably end up spending most of the lecture today talking about the lab, and if I finish early, I'll get into the next conceptual topic, which is control theory. So the objective of this lab is to use pulse width modulation, which we talked about earlier in the semester, to be able to play audio through a speaker on the board. And at the same time, we want to be able to control individually addressable LEDs that are on the board. So you might have noticed that on those boards, there's a grid. There's a 10 by 10 grid of LEDs on there. And those are really cool. Those are individually addressable LEDs. Back in the day, they used to call them neopixels, I think. But basically, you can control that whole grid of LEDs with one pin on the ESP32. I think it's kind of neat. So we want to do both of these things at the same time. We want to be able to control the LEDs and control the speaker. So we're dealing with two different peripherals. One of them is called the RMT, the remote control transceiver. I don't understand what the M stands for. Like remote, RMT. But anyway, RMT is the remote control transceiver. And we're using that to communicate with the LEDs. The idea is that was called remote control transceiver because it was designed to talk to IR remotes, which usually use a Manchester type coding system where you have a clock and then you have your data. And the signal, the way that you modulate the data on the clock is you do an XNOR operation between the clock and data. And what that ends up giving you is whenever you want to send a 1 bit on the data, you end up seeing a falling edge. And whenever you want to transmit a 0 bit, you have a rising edge. So in other words, it converts basically what Manchester coding does is it converts the data signal from a level sensitive to an edge sensitive signal, which is more suitable for IR remotes. And when you end up looking at the actual data that sent the modulated data, you can see that it consists of pulses of certain widths, right? So you have a wide pulse, short pulse, wide pulse, short pulse. And so the RMT peripheral is designed to set up these pulse trains, essentially. It just so happens, just by sheer coincidence, that the modulation scheme that's used by these individually addressable LEDs happens to be very similar to this Manchester scheme that's used for IR remote. So for that reason, we're going to adapt the RMT peripheral to communicate with these LEDs. Okay, and then the other thing, the other peripheral we're using is called the LEDC peripheral, and we're going to use that to generate a PWM, pulse width modulated signal. So basically, we're doing two different types of modulation here. We're doing a pulse width based, we're doing a modulation that's similar to an IR remote to talk to the LEDs, and then we're using the pulse width modulation, which is where you modulate an analog signal on top of digital, to talk to the speaker. Does that make sense? Okay, so again, this is a digital modulation, this is an analog modulation, essentially. Now the thing that's confusing here is that the name of the peripheral that we're using to generate the PWM signal is called LEDC, but yet we're not using it for the LEDs, we're using it for the speaker. So don't get confused by that. You know, the RMT is being used for the LEDs, and the LEDC peripheral is being used for the speaker, right? So the naming is kind of confusing there, right? Okay. So the objective, so on the board, I mentioned that you can control all those LEDs with one pin on the ESP32. So we have a pin on there, pin 33, and this is just a snippet of the schematic of the board. And you can see that the idea is that that pin connects to the input on an LED, and then there's an output on that LED that goes to the next one in series, and so forth. So it creates this chain very similar to a JTAG chain, or also, remember when we talked about daisy chaining SPI connections, the idea is similar to that, right? When you have a SPI, you have MOSI going out, and then the MISO coming out of the first and going into the MOSI the next, and so forth. This is the same idea, except we just have data in and data out, right? So we can control all these LEDs from one pin. This is a test point here, which you can use for debugging your design. You can hook this test point. This test point is a header that you can connect to the oscilloscope, so you can actually see the data in going into the first LED. Okay? Now, the way these are arranged, I believe, Alex can confirm this, but the two-dimensional grid is set up in row major order. So the bits are going to be shifted through the first row from left to right, and then into the second row from left to right. So the first LED that you send the bit to from the ESP32 is going to be the upper left-hand corner of the array, and then the lower right-hand corner would be the last one, right? So it goes through row major order.
Same way
Yeah.
they're arranged in the schematic.
Yeah.
Straight across, the PO goes from there.
Okay. Okay, and then we have separate. We have this audio circuit. So we have pin 14 rather, coming out of the ESP32, and that is going into this circuit, which looks a little bit more complex. But what's happening here is that we have this amplifier, the LM386 amplifier, that's used to amplify the signal, and at the same time we have some low-pass filtering going on in there too, because the pulse width modulated signal is like a square wave. And so if you send that directly into a speaker, you get some high-pitched, high frequencies in there, which you can eliminate with a resistor and a capacitor that are used for the low-pass filter, right? In addition to that, we have these potentiometers in here, which allow you to, you've probably noticed them on the board, they're like dials that you can turn. I think you have to use a screwdriver to turn them. But there are these potentiometers that allow you to dynamically adjust the gain on those things, so you can turn up the volume, basically. Okay, so, but the point here is that all of the signal is fed just by the one digital output pin on the ESP32, pin 14. Okay, and so we're going to drive pin 33 with the RMT peripheral, okay, to control the LEDs, and we're going to drive pin 14 with the LEDC peripheral to be able to generate audio. Okay, so let's talk about the LEDs. So as I mentioned, these things are designed to be connected in series, in like a chain. And you'll notice that there's no clock signal. So like if this was a SPI chain, of course there would be a clock and a slave select in there. In this case, there's just basically just data in, data out, right? So these use an asynchronous bus protocol. And the idea is that you send bits through here in a way that are modulated using these pulse widths, very similar to the Manchester coding I mentioned earlier, but it's a little different. In order to send a 0 in, you basically have the data signal high for a time and low for a time. And to send 1, you do the same thing, except the 2 times are different. So in order to send, so you have this basically time, you have time 0 and time 1. So time 0s are the 2 times to send a 0, time 1 are the 2 times to send a 1. And then you have high and low. So time 0 high and time 0 low are the high time and the low time in order to convey a 0 bit. Make sense? And likewise, time 1 high and time 1 low are the high and low times to send a 1 bit, right? So those are listed here in the table. So if I want to send a 1, I set the signal high for 400 nanoseconds, and then, I'm sorry, if I want to send a 0, rather, if I want to send a 0, right, I set the signal high for 400 and low for 850 nanoseconds. And likewise, if I want to send a 1, I have the signal high for 800 and low for 450. Does that make sense? Okay, so now what happens if I have it, let's say I have it high for 400 and then low for 400. Well, then the chip's going to be confused, right? It's not going to know how to interpret that, right? Likewise, if I have it high for 800 and low for 800, it's going to be like, what? I don't know what that is, right? So you have to maintain these specific high and low times in order to interpret, in order for the chip to interpret that as a 0 or 1, right? Now, you might ask, well, how does the LED know what a nanosecond is? That's a good question. It must have like an internal oscillator or something, right? Somehow, like it has a crystal inside of each LED individually, right? That can measure time somehow, right? But it's asynchronous. So you're measuring time on the ESP32. Obviously, it has its own clock, right, and timer. And so it has basically, think of the ESP32 as having its own clock, right? And each of the LEDs have their own clock. And so you're sending these pulses that are spaced out in real wall clock time, right? And then the LED recognizes those based on the time that the signal is high and the time that it's low. If you screw up and you violate these timings, like I said earlier, if you have 400 high, 400 low, then I don't know what it does. Probably just doesn't do anything. Probably just ignores that, I would imagine. I haven't tried that, but so the idea is that you want to stick to these shapes, essentially these two shapes. Now, on the other hand, if you have the signal low for a long period of time, 50 microseconds, and you might say, well, how's 50 microseconds a long? Well, it's long compared to nanoseconds, right? Then that means something special too. That means that you want to reset. Okay? So the idea is that these LEDs have that can light up with 16 million different colors, right? There's 8 bits red, 8 bits green, 8 bits blue. So what they're expecting to see from you is 24 bits that are just shifted in to the data in, right? Once you've shifted in 24 bits, they will light up in that color, at which point they will switch into this state that they will ignore all subsequent bits for the purpose of setting their color, but they'll pass through, right? They'll forward any bits that they receive. So in other words, what this means is when you have these LEDs arranged in a daisy chain, you can set the color only of the first one initially, right? And then once you set that color, you can set the color of the next one in the chain, and so on, right? So basically, you can program the color of each one of these LEDs one at a time, starting from the one that's connected closest to the chip that's programming the colors, right? And so now the idea though is that because these times are so small, as a human being, you don't see the colors changing sequentially from left to right, basically. You can update the colors so fast that it's not perceptible as you're looking at them. So you can actually play a video where you have different frames coming up to form the video, and the frames are actually changing. Now, technically, if you were to slow things down, the frames are changing 1 pixel at a time from left to right, but you can update them so fast that you don't actually see that happening, right? It looks like it's instantaneous, but it's not, right? Now, the problem is that after you update your frames, you want to be able to, after you set the color of all the LEDs, then you want to change the color of the LEDs, and this is what the reset period is for. You basically, after you program the color of all the LEDs, you chill out for 50 microseconds and don't do anything, at which point you can repeat that process. So after the reset signal is received by the LEDs, they go back into the mode where they're looking to update their colors. So any bits they get, they'll use to update their colors. But in the meantime, they'll maintain their old color. Okay, so just to be clear, when you power up the board, and you guys obviously know this because you've powered up the board, the LEDs are off, right? If you program the colors on the LEDs, and then you go into this reset phase where you tell them, okay, I'm done, they will maintain the color that you program them with last. So they maintain whatever the last color is that you program them with, right? Does that make sense? But you have to, in order to reprogram the colors, you have to have at least 50 microseconds of this downtime, right? So I mentioned in the lab sheet, I mean, this is not really, probably not super relevant, but this basically is one of the things that limits the number of LEDs you can have. Because if you have, like, for example, if your goal is to update the LEDs, 30 frames per second, 30 times per second, right? Within that 30th of a second, which is 33 milliseconds, right? You have to budget time for that reset as well as time for shifting all these bits through, right? So at some point, once you take the frame time and you back out the reset time, then you only have a certain amount of time left over where you can program the LEDs. And the programming time for all the LEDs is a function of how many LEDs there are, right? Because they're programmed one at a time, right? So I mentioned in the lab sheet that, like, given these parameters, you're limited to basically like a 300 by 200 array of LEDs or so, assuming that you're trying to update them at 30 frames per second. Of course, you can not update them that fast, but if you're playing a video, generally you're at 30 FPS, right? Okay, so that's how those work. Any questions about that? Now you might have noticed here that with these times, it's probably not practical to bit bang these with software, and this is the reason why we're using a dedicated hardware peripheral to modulate this signal, this bit train, the bit stream, whatever you want to call it. Okay. All right, so how do you set this up? So I mentioned we're going to be writing a low-level driver for both these peripherals. So if you use any existing driver, then you won't be fulfilling the requirements of the lab, right? We want you to write this one. This is the only one we're going to do at low level, right, where we're writing to registers. Okay, so first of all, by default, the ESP32, or when I say by default, I mean when you power up or reset the ESP32, it's going to disable all these peripherals. And so in order to turn them on, there's two relevant registers here. These are global registers. These are not specific to the peripherals. One's called system perif clock enable reg, and the other one's called system perif reset enable reg. So the first thing you want to do is find the two bits in these registers that match up to these two peripherals that we're targeting, right? The RMT and the LEDC, right? And so you can see them in here, bit 11 in both. It just, these two registers line up. They have the same, the bits are mapped to the same peripherals. So you can enable the LEDC with bit 11 and you can enable the RMT with bit 9. And you'll notice too that it shows, actually the bottom row shows the reset state. So actually I was wrong. Some of these peripherals are actually enabled when you reset the system, but I think most are not. So the LEDC and the RMT by default are disabled, so you're going to want to turn those on. So you just have to write a 1 bit into each one of those guys. Make sense? Now, this goes back, it's been a little while, but do you guys remember we talked about how to turn on bits without affecting the other bits, right? So we're going to want to make sure that we turn those on without affecting the other bits in there. We only want to flip those two. So that's for enabling, and then you can also, there's a separate reset, and you want to take them out of reset. Right? So, Alex, when you turn these guys on, does it make the reset high and then you have to set it low? Or because according to this, the reset's low by default, right?
Yeah, it doesn't affect the reset at all.
Yeah, okay.
When you turn those on.
So our instructions always say enable the peripheral, step 1, and then step 2 is take them out of reset. But I don't even think you have to take them out of reset, right? You probably just have to enable them, right?
I always pulse that high and then back low again to make sure it's reset, but you probably don't have to do that. I've never tested it the other way.
Yeah, so our reference code pulses the reset, right? Sets it high, sets it low, right? So that way enable first and then pulse the reset to reset. So basically what you're doing is you're pulsing the reset signal to those two, circuits on the chip that correspond to those peripherals. Okay? Okay, so these two, you only have to do that once on setup. Now, by the way, in order to do that, you just have to know the addresses of those two registers, and we give those addresses to you in the lab sheet. These numbers here are actually offsets. These are addresses, but they're not the absolute address. These addresses are relative to a base address that has these registers in it, right? Which are called with the system space or system base. So there's a system base address, which you can look up in the manual. And then what you're doing here is adding 18 and 20 in hex to that system base address in order to get the absolute address of these two peripherals. Okay, but I just give you, in the lab sheet, I just give you the absolute address for these two guys. I have a table in there.
If you forget to turn on the peripheral like this before you try and write to some of the peripheral registers, your writes will not stick. So make sure you do this, or else you'll be wondering why your writes aren't taking effect. So very important.
Yeah, I suspect the reason why they're off by default is to save power. It's power efficiency.
So especially like Bluetooth and Wi-Fi, if those were all by default, power consumption would go through the roof.
Yeah, I think so. I think it actually, they're power gates or clock gates, those things, when they're disabled, those two peripherals. Okay, so, once you've done that, now you have to start dealing with registers that are specific to the peripherals that you're talking to. So for the RMT, the first one of those is called RMT sysconf_reg. And again, this address here is a offset into the RMT register base address, right? So again, that's not the absolute address. Okay, so in here, now again, you can see that there's bit fields, and some of these fields are multiple bits. And if you look at the bottom row, those are the default values, the reset values. Now, generally, you don't have to change. If the reset value is the value that you want in there, you don't have to change that bit, right? So you'll notice that, for example, clock enable is 0 by default, right? Which is, obviously that's not good. You want to enable the clock if you want to use the peripheral. Now you might want to say, wait a minute, I thought we just enabled it in this register. Why do we have to enable it twice? I don't know. It seems kind of dumb to me, but we have to enable it twice. So this is a separate clock enable, right?
That clock, so the clock we enabled before is like the master clock that clocks the RMT peripheral itself so we can access it. This is the clock that drives the bit stream that's coming out of the RMT peripheral. So it's two separate clocks.
Okay, so one of them is like the internal logic, and the other one is the actual pin, I guess, the driving, the pin drive. Yeah, okay. But yeah, so there's two.
Before we continue, might it be good to show a diagram of the RMT so people can kind of see what's going on here? Because I could see this being kind of confusing if people don't.
I don't know if I have a diagram of the RMT.
Oh, really? Okay.
I'm not sure if that would help much, though.
Okay.
And I mean, because a lot of those diagrams tend to be pretty busy.
Yeah.
to say the least. Well, so there is a so the RMT. So the idea here is I'm presenting this just like as the programmer interface, how you talk to it, what the hardware software interface is, and that's mostly going to be done through these registers. So really, what this is all about is figuring out which fields of which registers in which order you want to write in order to get the peripheral to do what you want it to do. So I have a few, and there's not many. There's only 4 registers, I think, here. There's the 2 global ones, and then I think there's 4 registers associated with the RMT. So this one is the first of that. So you've got the clock enable, and then there's a reserved range here, 30 down to 27, so you don't write to that. There is the S clock active, which is, that sounds good, right? And that's 1, so probably don't want to mess with that. Then there's RMT S clock select. So this one is selecting, so on the ESP32, there's a few different clocks that you can use to drive these peripherals. Generally speaking, we always use the one called the APB clock, which is the 80 megahertz clock. And that one, in order to use that one, you actually have to change this to 0. It's 2 bits, 25 down to 24. So you're going to have to change this one to 0. I think if 1 is in here, it's using the 1 megahertz clock, I'd imagine. So we want to use the higher speed clock so we can get more fine-grained timing out of this thing, which, you know, is, I mean, you might be able to use the 1 megahertz clock because we're dealing with 1 megahertz is a nanosecond, and these timings are hundreds of nanoseconds. So I guess technically we could, but we always use the 0 clock. We zero this one out to use the 80 megahertz clock. And to keep that in mind, whenever you make any calculations, it's based on 80 megahertz, right? Am I right? 1 megahertz is 1 nanosecond, right? Yeah, gigahertz is a picosecond, megahertz is a nanosecond, yeah. Okay. So we always use 80 megahertz, which might be overkill, but we always set that to 0. Okay, then we have this clock divisor, right? So you have the 80 megahertz, you start out with the 80 megahertz, and you can divide it down. So in this case, we're not going to use the divisor. We're just going to not divide the 80 megahertz clock. We don't want to divide it, right? So you'll notice that there's a 1 in here by default. And you would think that a 1 would mean that you divide by 1, which means that you don't divide, right? Dividing by 1 doesn't do anything, right? However, whatever value you put in, it actually adds 1 to for some reason. So you actually have to put 0 in here, which you would think would divide by 0, but it actually is just dividing by 1. So you have to set this guy to 0, right?
Yeah, and I don't think it says that in the manual. So if you're looking at the manual, I'll
yeah.
have to figure that out.
So you have to put a 0 in here for this, right? And by the way, these values are all in the lab sheet. I'm just describing them here, but when you look at the lab sheet, it'll actually explicitly say, you know, set 0 there. Okay. And then we have RMT MEMForce PU. That one's fine the way it is. RMT MEMForce PD, RMT MEM clock force on. I think that's okay the way it is, right? 0, 0, 0 for those. The only other one that we want to turn on here is the RMT APB FIFO. Well, actually, this one's fine too. This is by 0 by default. So this is so Alex likes this new feature that they have in the ESP32-S3 where it has a FIFO built in. But last year we didn't use the FIFO, so I just assume this year we'll just do it the same way we did last year and not use the FIFO. The FIFO is disabled by default. You can see 0 on there. So you could just leave that one alone. In the lab sheet I say to set it to 0, but that one should be 0 by default. Everyone with me? All right. Okay. All right, that's the first register. The next register is called RMT channel N conf 0 reg. Okay, so this one is has a variable in the name of the register N. So there are 8 RMT channels. The first 4 of the 8 are for transmitting only, and the second 4 are for receiving or transmitting and receiving, one of the two. We're using channel 0 because we just want to transmit. We don't care about receiving, right? So that value of that N is 0 for us. We're using channel 0. The problem is that if you search in the technical the reference manual, and by the way, that's linked on the Dropbox. You guys have probably seen that, right? You can search the reference manual. It always refers to that as CHN. Right? And so that's how you have to search for it. If you search for channel 0, you won't be able to find it. What's even more confusing is sometimes instead of N, they'll use M, and sometimes they'll use X for those variables. So in this case, it's N. And again, you can see the address there. That's an offset. There's actually, the N is part of the offset too, because there's a separate one of these registers for each of the 8 channels. Right? So in order to calculate the address of this, you have to multiply by the channel number, or in this case it was 0, so it's not a big deal for us. Okay, so there's a few fields in here you want to change. There's RMT carrier enable. This one you actually want to set to 0. The reason for that is, you remember I mentioned earlier this Manchester code, right? So when you do Manchester encoding, you actually take the clock and you XNOR it with the data. This is how the data is carried over the clock. With the RMT, we don't want to do that. So, or with the LEDs, we don't want to do that. So you want to actually turn off the carrier enable, make that one 0. Then we have the RMT div count. Now this one is our, this is the divider?
Yeah, the other
right?
one looks like a global divider, and this is a
Yeah.
local divider.
It's a local divider, right. So we're going to set that to 0 though, right?
Either 0 or
1.
I forget if this one is the weird thing where you add 1 or not.
It might, I think it might just be, I think it actually is 1. Yeah, I think that's 1.
Yeah.
So this is another divider. Now you might say, well, why? Okay, there's 2 dividers. But normally I would have expected the default to be 1 there, but it's not, it's 2. So that's why I've got it highlighted. You want to change that. Okay. And then there's RMT idle out enable. This one you want to set to 1 actually, because if this is set to 0 and you're not actually using the RMT, I think it tri-states the pin, right? It turns the pin off. If you set this to 0, it will explicitly pull the pin low when you're not using the RMT, and we're going to take advantage of that in order to enable the reset capability, right? That reset when the line is down for 50 microseconds, it resets. So this bit is actually what enables that reset capability. And then RMT mem transmit wrap enable. This one, Alex turned this one on. I don't know why we want to wrap I don't know if that's important or not.
My reason for doing that is because I was using the FIFO, and so
Oh.
when you're putting stuff in the FIFO, it wraps around to the beginning of memory again. So I wanted the transmitter to
Okay.
keep wrapping.
So we might want to leave that 0 then.
It depends on how they're doing it, how they're filling up the memory, I guess. But maybe it depends on how they've designed it.
Okay. Okay. Well, I'll clarify that in the lab sheet. I think that one you can leave at 0. And then finally, I'm going to come back to this one, RMT config update. So this one you're supposed to write to 1 whenever you make a change, right? So I think you have to write this last, right? So whenever you make a change to this register, you want to set this bit to 1 in order to register your changes. Right? Is that right?
Yeah.
So you want to do this one last. Okay? Alrighty. So that's register number 2. Okay, so the way the RMT works is that was basically for setting things up. Now, by the way, there is a I'll mention this, hopefully I don't make things even more confusing. There is a config 1 register for channels 4 to 7, but not for 0 to 3, as I learned recently. So there's no config 1. We used to have one last year. We had a config 1 register with the but one of the changes they made in the ESP32-S3 is they dropped config 1 for channels 0 to 3. So that's, yeah, so in case you see any reference to config 1. And there is a config 1 for the LED peripheral too, by the way. So that's another reason that might be confusing. Okay, so you might say, and by the way, the reason config 1 and config 2, that's just so we can have 64 bits of total, configuration bits, because there's only 32 bits per register. Okay, so the RMT, so it's the way it works is it basically follows a script. And what the script is a set of entries where each entry is 32 bits, but it's divided into 2 halves. The first half is the first phase, and the second half is the second phase. So what I mean by that is when you look at the WS2812 LED protocol, this encoding scheme, it always is high and then low, right? High, low. So the RMT is programmed the same way, where you basically tell it how many clock cycles, not seconds, this is seconds, right? It doesn't know seconds, it knows clock cycles. But we're at 80 megahertz, right? So you basically say how many 80 megahertz clocks you want it to be high and how many you want it to be low, right? And that goes into one entry in the script or with the RMT RAM, right? And so when you put that in, you're basically just telling it how to transmit one bit, right? And so you're going to want to have 24, if you put 24 entries in this RAM, you're basically saying high for this low, high for this long, low for this long, high for this long, low for this long, and so on, 24 times. And that will program the RMT to send out 24 bits using this encoding scheme. You guys with me? Now, you might say, well, I mean, you have to put the number of cycles in for each one of the high and lows? That seems wasteful. I mean, if you just tell it how long, yeah, I mean, that's just kind of a conceit of the peripheral, right? You have to explicitly have, even though there's only 4 different options here, right? You have to put in, the cycles for high and low for every bit, right? In other words, the high and low cycles is 15 bits for each one, and it really only needed to be 2 bits because there's only 4 options for that, right? But obviously the peripheral is general purpose, so you have to explicitly put in, the high and low time for each bit. Okay? So what you're doing here is to program one LED, you're writing 24 entries into this RAM, which is a script that then the RMT will run through and use that to drive the pin with that sequence of bits, right? So every time you write one LED, you have to write 24 entries to this RAM that tell it how to send the color out to that LED. You guys with me? To each LED in sequence as they're connected in series. Okay? And the software your software will have to tell it, when to go, when to start that process, right? Okay, and it will also have to check to see when it's done because your software may be fast enough that it may want to send the next color before the previous color finishes, right? Okay, so that's what the RMT RAM is. So it's basically a set of addresses, it's basically just an array of 32-bit words where each word consists of a level, which in our case is always going to be 1 at first, then a 15-bit period, how many cycles you want it to be high, followed by the next level, which is always going to be 0 in our case, and a 15-bit number of cycles for the low time, right? And the old ESP actually had allocated 64 of these entries per channel. But the ESP32-S3 has reduced that to 48. So you actually only have 48 bits you can send out at a time with the RMT, right? Assuming you're using all the channels. If you're using one channel, I think you can use all the RMT RAM for one channel. Can you still do that?
Expand it.
Yeah.
A bit field.
But there's only, even if you do that, there's only 384, right? Which is 8 times 48. So there's 384 of these 32-bit words in the RMT RAM. Now the RMT RAM, the way that you access it is the same way you access any control register, right? You're just gonna, write to it like you would any other control register. Okay, and then also it's 0 terminated. This is the thing that I was hung up, when I first wrote this, I got hung up on this for a while. You have to make sure that after the last entry, after the last bit, after the 24th bit, you put a 0 in there. So bit number 25, well actually index 24, so 0 to 23 is going to be your 24 bits. And then index 24, which is the 25th bit, is going to be 0 that tells it to stop. Okay? So don't forget to put that in there because I got hung up on that for quite a while. Okay, any questions about that? Okay. Okay, so then in order to basically just tell it to go, there's another register. Oh no, it's this RMT channel 0 config 0. Is this the same one? The same, oh sorry, it's the same register as before. It's just a new picture of it, right? So this is the same register I was talking about before, except before I was talking about setting things up. Now, this is the way that you actually get it to go. This is not part of the initialization process anymore. This is how you say, go, send your bits. So there's a bit down here called RMT transmit start. So you just write a 1 there, and it'll tell it to initiate the process of sending the data out, right? So again, this is the same register we had before. It's just, this is kind of like the normal operation part. And then there's the update. Do you have to call the update after you start, or? I don't think so.
The technical reference says whenever you change anything in the register, you have to
Yeah.
set that bit.
So it's, so I know you had it in there, but I thought maybe that might not have been necessary, because I don't remember doing that last year. But
that bit didn't even exist last year. That's a new S3 thing.
So in order to start, you'd have to write that bit and then this bit, right? So bit 0 sets to 1, bit 24 set to 1, right? And that just causes it to dump the data out to the LED. So every time you set that bit to 1, it's going to update one of the LEDs. And so you're going to want to do that, obviously, 100 times to update all 100 LEDs. Okay? Okay, and then finally, the only other thing you need to know is when it's done. Because how long is it going to take to do all that? Well, let's see here. So if you look at this waveform, to send a 0, you have to add 400 and 850, right? And likewise, to send a 1, you add 800 and 450, right? So either way, it's 1,240 nanoseconds, so 1.25 microseconds per bit, okay? And then in order to send, remember, you're sending 24 of those, so it's going to be 24 times 1.25 microseconds, which is a decent amount of time. So your software is probably going to have to sit there and twiddle its thumbs a little while that happens, right? It's going to have to wait. You're probably going to want to poll and keep saying, are you done yet? 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 Right? So that's what this next register is for. It basically just tells you when it's done. So there's this RMT interrupt raw reg where it'll set the bit 0 to 1 when it's done, right? And then you have to clear it by setting bit 0 in the clear reg. Why you can't just write to this reg to clear it, I don't get it. But obviously this one's read only and this one's write only, but it could have just made one register that was read write. But yeah, but anyway, there's two different registers. One is how you check to see if it's done, and the other one is how you clear the done status after the software acknowledges that it's done. After your software acknowledges that it's done, right? After your software notices it's done, then you clear it, okay? All right, so that's not too bad, right? It's basically, the RMT is essentially you've got the two system registers there to turn it on. Then there's this config reg. That's really the only register you use to interact with it. There's the sysconfig reg and then the config 0 reg, so there's two. Then there's the RMT RAM, and then there's that interrupt, right? So that's kind of just summarizes the whole thing. Now in this case, remember that we're using the 80 megahertz clock, and we're not dividing it. There were two opportunities for us to divide that clock, and we didn't take either one, right? We used a one divider in both cases. So the clock is 80 megahertz in the RMT. Everywhere you deal with the clock, you're assuming 80 megahertz, right? Now, unfortunately, that's going to change a bit here in this next peripheral. So let's go to the LEDC. Okay, so the LEDC is a little bit more complex. A few more registers on this one. The reason for this is that the LEDC is it's comprised of really two peripherals. There's a timer and there's the LEDC. The timer is what basically counts, right? It takes care of the clock dividing, and it's like the clock. It's like the wall clock, right? The LEDC peripheral itself is used to look at that clock and then figure out how to set both the period and the duty cycle. You guys remember the piece pulse width modulation has a period, right, which is basically just the repetition rate, right? And then there's the duty cycle, which is what percentage of that period the output is 1 and, output 1, right? So you can have like a 10 kilohertz PWM signal, right, that's running at 10 kilohertz, and then you can have an 80% duty cycle, meaning the clock is high for 80% of the time, right? So make sure you have that terminology straight. There's the period or the rate, right, of the PWM, and then there's the duty cycle. The duty cycle is actually the value that you're modulating onto the PWM. The period is just the speed of the signal, right? In some applications, the period isn't really too important as long as it's fast enough, right? But the duty cycle is the important thing. That's the actual signal that you're using, that's being conveyed, right? You guys with me? Okay. So so there's a register here called LEDC timer X. Again, X. They're using X now. So we're going to use 0 for X. We're using timer 0. Okay, so this one has, this one's pretty important because this one is what is controlling the period of your PWM. So you've got, let's skip this one for now. LEDC timer reset, that should be 0. Okay. Then you have this thing called LEDC clock div timer, 0 in our case. Remember, X is 0, right? So this is actually an 18-bit field. This is a big field, but it's using fixed point representation. Do you guys remember fixed point? We covered that in 611. So the idea is that there's 18 bits here in total, but 10 of the bits are whole bits and 8 of the bits are fractional bits. Okay? So this is the divider, the clock divider, right? Now remember, with the RMT, we did not use the clock divider. I mean, we had a clock divider, but we just set it to 1, right? We just kind of ignored it. In the case of LEDC, we're going to use the clock divider because we want the 80 megahertz signal to be divided down into a period or a rate that actually matches the audio sample rate, right? So audio files can be in different sample rates. Typically, like, well, it used to be there were always, most digital audio is 44.1 kilohertz or 48. I think 44.1 was CD quality audio, right? 48 kilohertz was studio quality, right? I think even to this day that 48 kilohertz is kind of the standard. The problem with us, though, is that we're limited, we have very limited memory on this thing, right? So we don't necessarily want to use 48 or 44 kilohertz. We want to use a lower sample rate, just because we want to be able to fit. The higher the sample rate, the larger the file size, especially since we're using, we're recording this as raw audio. It's not compressed as like an MP3, right? You guys with me? We're doing lossless video or audio. Okay? So now we have a script that we're going to give you that will take a MP3 or WAV file and it will convert it into just an array of samples in C. Okay? However, the sample rate is going to depend on what file you give it. Okay, so Alex took, when he did this, he took Sandstorm, the Sandstorm audio, and I think he used Goldwave or an audio software to downsample it to like 8 kilohertz, I think it was.
Yeah, I used Audacity.
Audacity, I'm sorry, I always forget. Audacity. Audacity is a open source audio software. He used Audacity to bring Sandstorm down from its native 48 kilohertz down to 8 kilohertz, right? Just to reduce the size. You guys with me? The point is, though, is that when you read the file, the audio file, the sample rate is going to be revealed to you, right? The script will give you the sample rate, And if it's too high, you may want to go into Audacity and reduce that, right? But the sample rate is a what I'm trying to say is the sample rate's a variable. We don't know what that is. It depends on what sound you want to play or what file you want to play, right?
Yeah, you don't actually have to do anything in Audacity anymore though, because I updated the Python script. So now you can just specify a sample rate and it'll automatically downsample it to that. And if you don't specify a sample rate, it will automatically downsample to the point that your entire audio file will fit into memory.
Okay.
So you don't have to use any external programs anymore.
Okay, good. But the point is, it's still a variable. You don't know what the sample rate is. So this, where I'm going with this is this field is the way that you convert from 80 megahertz to whatever sample rate your file is, right? Or whatever file whatever converted to, right? So what you want to do is take 80 megahertz and divide it by the sample rate, and that's going to give you the divider, right? The clock divider. You guys with me? Now that number is probably going to be a fractional number because your audio sample rate is not going to be an integral multiple of 80 megahertz most likely, right? So in your software, when I say your software, your ESP code, you're probably going to want to do that divide as a floating point calculation, right? But you have to convert it to fixed point before you put it in here. You guys follow me? Right? So the way you can do that is you treat this like two different, it's only one field. This part is a little confusing because in the control register there's only one field, but really it's two. There's the whole bit and the fractional bit, right? And Alex's code explicitly puts both in separately, right? So Alex treats this as two fields, even though it is one field in the control register. And so in other words, you can calculate the whole bits by essentially doing your division, 80 megahertz divided by your sample rate for your file, and just rounding it down, right? If you round down the division, that's the whole part, right? And then the fractional part, you can calculate by taking the fractional part, isolate the fractional part, and you multiply it by 256, right? Because there's 8 bits here. And so what we're showing is this is in the units of 1 over 256, right? So this, if you treat this like a separate field, it's like how many 1 over 256 are part of your fractional number, right? So for example, if your fractional part of the divide is 0.1, then you're going to divide that by 256 and you're going to get 25.6. And of course you have to round that down to 25 and stick 25 in this 8-bit field, right? So you're still going to have some rounding here, right? Because you can only get within 1/256 of the actual quotient, right? The ratio between 80 megahertz and your sample rate, okay? So that's what you're going to put in here.
Last year, I don't think a single person actually computed it in their codes. Everybody just did it like hard coded it, did it manually whenever they changed their sample rate. Please don't do that because it just makes it way more painful for you. Please just compute it in your code. It's way easier that way.
See, now when I wrote this originally, I didn't see any need to have one PWM period matched directly to one audio sample period because I figured, well, the PWM signal could oversample, right? Like I could send 10 PWM periods for every one of the actual audio samples stored in the file. So that's how I did it. But I think Alex's approach is better to create this marriage between the PWM periods and the actual samples as they're stored in the audio file by syncing those up, right? So what we're doing is we're syncing up the PWM with the actual audio encoding format, right? Is the idea. Okay, and then, so that's what that is. So that's an important field. Then there's the duty resolution, okay? So this is the part this is a little weird too. So this is going to define, this is the factor for converting the 80 megahertz APB clock to the PWM frequency, right? But within that period, within that PWM period, the hardware is dividing that up into segments. It's subdividing each PWM period, right, into its own clock, right, where it's counting for each PWM period. It has to count. Why? Because that's how it calculates the duty cycle, right? So what this is we always put 8 in for this, right? The duty cycle resolution is 8, which stands for 8 bits, which means that the duty cycle, the PWM period, when you're calculating a duty cycle, we're going to give it 8-bit resolution within that duty cycle, which means that the duty resolution, the duty cycle can be one of 256 values, which means that the audio sample depth is 8 bits, right? Now, most digital audio on MP3s and on, normal digital audio is 16-bit, right? But again, we're going to use 8-bit, right? And your software takes that conversion too. Yeah. So like if you open up a WAV file, each sample, actually nowadays they're using, I think really high quality audio uses floating point numbers for the samples, but we want to use just 8-bit integers. So that's what that field, that's the duty resolution, is essentially what value the hardware is expecting, what width value the hardware is expecting for you to put in as the duty cycle. In this case, 0 to 255, right? So the duty cycle is 0 to 255, which represents a duty cycle of 0 to 100% on the PWM signal, right? So we're going to map a value of 0 to 255 to a percentage of 0 to 100% for the duty cycle. So these two fields are really just defining the PWM frequency and the resolution of the duty cycle value that you want to put in, which is the same thing as your audio resolution, your audio sample size, right? Okay?
By the way, the reason we're not doing 16-bit is, well, there are a couple of reasons. One, the ESP doesn't even support going that high. It caps out at like 12-bit.
Yeah, you can see it's only 4-bit field, so you only got from 0 to 15.
And also, it only, like, we couldn't even do 12-bit at these frequencies, I don't believe, because that counter would overflow too quickly at higher frequencies. So there's a formula in the data sheet that you can use to actually see how high you can set the duty resolution for a given clock divider value. It's kind of interesting.
Okay, so this register has like pretty much all the important stuff in it. And then there's this, finally, I'll come back to this one, LEDC timer X para up. This is, I think, equivalent to the update bit of the other one. So you have to set this last to have it accept your changes. So you just write that bit last. Okay. Okay, then we have, now keep in mind, this was called the timer X, right? Then there's another one called channel 0, LEDC channel 0 config 0 reg. So this is just yet another control register, but this one doesn't have anything super exciting in it. It's pretty much just, this is the way that you connect the timer to the LEDC channel, right? So we use timer 0, and so obviously you want to put 0 here because this is what connects the timer 0, which is we just configured timer 0. This connects it to the actual LEDC peripheral. So you want to put 0 there, but it's 0 by default, so I don't think we need to change that or not. This one's signal out enable. That should be set to 1. So that one you definitely want to change. And then again, para up just updates the changes. Okay? All right. And then there is a config 1, finally. So there's a second configuration register. And the only thing this one is used for is basically telling it to start. Duty cycle, this starts it up, right? This just triggers the thing, turns it on, makes it start pulsing. Okay. All right, now finally there is a register here called duty reg. Now this one doesn't have anything other than just the duty cycle. This is where you're just putting your sample from your audio file. You're just sticking it in this register. But it's 19 bits. We're only using 8, right? Is it the lower 8?
Yeah, it's the lower 8.
Why do we have 19 bits?
Might the S3 go higher than 12?
I don't know.
The regular ESP goes to 12. Maybe the S3 goes higher.
Maybe it goes higher. Yeah, because Alex just got done explaining that there's no way that you can have more than 12 bits.
Regardless,
but
still at our clock frequencies, you still can't use all of them because the counter would keep overflowing.
Yeah.
But maybe it does go to, I'll have to look that up.
So don't get confused. There's 19 bits, but obviously we're not going to put anything bigger than 8 bits in there. But this is where you just dump your audio sample. Just put it in here. Okay, and then finally, I didn't show it here. Okay. I didn't show it here, I'm sorry, but there's also an interrupt raw and an interrupt clear for the LEDC too that allows you, the software, to know if it's done. Is that triggered after one sample, one PWM period? Is that how that works?
Yeah,
okay.
There's one that gets triggered every single time.
Okay. Right, so, yeah, that's going to be, that's going to put a little bit more load on the processor because you're going to want to update that every sample at 8 kilohertz, right? Or so, or whatever your audio file is. Make sense? Everyone with me? So I know that was a lot of stuff. But we have all that in the, we have it all enumerated out in the lab sheet, which, like I said, I'll post right after class today.
What about the IO mux?
Oh yeah. Sorry, there is one more thing that we need to know about the setup. I skipped it earlier. Okay, so there is also, I actually talked about this at the very beginning of the semester briefly. So the ESP32-S3 has 56 total pins. Of those, 45 of them are, I guess they're considered GPIO. They're user programmable pins. When you boot up the ESP32, none of those pins are connected to anything by default, I don't think, right? Unless the firmware sets up some of them, like if there's a boot firmware or something. But generally speaking, these 45 pins are supposed to be for you to set up, right? And the way you do that is through, there is a GPIO matrix and there's an IO mux. So I don't know if you guys remember this, but the GPIO matrix is, there's one of these for every pin. So basically, all 45 pins have a multiplexer. So there's 45 of these multiplexers that allow you to connect internal signals that can be used for output and send them to the pin as output. Now, likewise, there's also the reverse situation for inputs, right? So there's an output mux and an input mux for every pin, because I think just about most of the pins can be used for input or output. You guys with me? Now in this case, we're only doing output, so don't worry about this. Don't worry about the bottom part. We're only worrying about output. So when you do output, there's a GPIO matrix that basically just allows you to connect a peripheral signal to a pin. So to select a pin, you have to select the right control register for the mux. Every mux has its own control register. They're enumerated, right? So in other words, in order to select a pin, what you're really doing is selecting an address, a memory address that corresponds to this multiplexer. Once you've got the memory address, then you just program what you want to connect to that corresponding pin. So in other words, if I want to connect pin 10, say, to the LEDC, I have to find pin 10's address for its mux, and then I just put whatever the code is for the LEDC into there. Right? You guys with me? Okay. Now the problem is that that's not alone is not enough, because there's also the secondary mux that the primary mux has to go through, and this is the kind of a shortcut for high-speed peripherals. So each pin has like an intended purpose that you could use to basically bypass this and connect it to one of its, specialty purposes. In our case, we're going to set these guys to 0, though, right? I'm sorry, to 2 rather. 2. You set the select here 2, which just uses the GPIO mux, right? You guys with me? So in other words, we just want this guy to pass through, right? We don't want it to intercept this guy. Okay? But unfortunately, that means there's 2 registers you have to update. You have to update the GPIO and the mux and the IO mux. You guys with me? Okay, so how do you do that? It's pretty simple. There's a function. There's a register called GPIO funcx, where the x is the pin number. Now remember, there's 48. It's so confusing because
I think they're labeled 0 to 48. So.
There's 49. Yeah, they're labeled 0 to 48. There's 49. 49. I think only 45. Anyway, but anyway, they're enumerated 0 to 48, right? So what you have to do is basically find the right one and put the right function in there. And there's a couple other bits about inverting and enabling and that kind of stuff. We have that in the lab sheet. And then finally, the same thing with the IO mux. You have to make sure you put a 2 in the IO mux so you can pass that guy through, right? Make sense? Okay, and again, this will be in the lab sheet. One of the things they often do here for these guys is the name of that register is GPIO func pin number out select config reg, right? So you can actually do this thing where you can define a pin and then you can have another define that includes that pin number in the name. It's kind of neat. You just use this double £sign thing. So for example, in this case, we have the GPIO base, the IO mux base, pin 12, and then this guy can actually take pin 12 and incorporate it as part of the define. And you can also use the pin here as part of the definition of the define to calculate the address. That's just a kind of a trick to set up these constants for the address. And then remember that we're using reg clear bit and reg set bit, essentially, to set all of these registers, these control registers. Okay? So this now in this case, really quick, just to give you an idea, that mux, this guy, the GPIO matrix, there's a special input called 256 that's used for GPIO. So that's the way you could just have the software bit bang. Like if you're doing bit banging, you just want to write a value, you're going to use 256, right? That allows you to just send a 0 or 1 as determined by the software.
That's your digital write. When you write digital write, that's how it was working.
Right, but in this case, we don't want a digital write because that's bit banging. We want to control the pin with the peripheral, the RMT or LEDC. So we want to use the codes for those, which I have in the lab sheet. We have the code. So there's codes for LEDC and RMT, of course, which channel of each as well. And those are codes for the GPIO matrix. Okay, and then finally, last thing I want to mention, it looks like we're out of time. Last thing I want to mention is what are we doing with the LEDs exactly? What is the purpose of the LEDs here? We just want to use the LEDs to visualize the sound, right? We want to use them as a visualization tool to basically, light them up depending on the amplitude of the sound, and we have details on that in the lab sheet. Okay, any questions? Okay, sounds good. I will post that and after class, and then I'll let you know about Thursday because I have some conceptual stuff I need to cover. I'll send an update about Thursday's class, whether we're meeting here or in the lab. Thank you.